Okay, everybody, I want to welcome you to our astronomy meeting tonight. Tonight we have a very special guest, Miss Mia Della Reyes. Mia is a undergraduate student in over at NC State, my alma mater, so she's in one of the best schools in the area. So what she's going to talk about tonight is observing galaxy evolution at intermediate redshifts. So I'll read a little summary here. Galaxies are among the most basic building blocks of the universe. However, despite decades of study, we still don't fully understand how galaxies form or evolve over time. One way to study galaxy evolution is to observe how global properties of galaxies, such as their masses, star formation rates, and chemical compositions, change over time. In this talk, she will present some of her past and current work on using spectral data to measure these galaxy properties when the universe was half its current age. Mia she has a major in physics and math at State. When she graduates, she will be going abroad to the University of Cambridge to do a one-year Master's of Philosophy, then come back to the U.S. and find a PhD program in astronomy. So with that, I will turn it over to Mia.
Okay, well, thank you so much for having me today. Let's see, as you probably guessed from the survey or from the summary, galaxy evolution is complicated. This is the one thing I want you to take out of this talk. So I put it nice and big on the title slide. So the general premise of this is that studying galaxy properties tells us something useful about how galaxies evolve. Right, so people study galaxy evolution in different ways. Some people try to model it from the very beginning, like right after the Big Bang, to see what happened to galaxies and see if they can match what kinds of properties we see today. But what I do is sort of working backwards in time. So watch galaxies change in the past and see if that tells us something useful about how they came to be this way. So I'm sure many of you already know this, but galaxies are basically made up of gas and stars. And there's some other stuff too. There's dark matter and dust and stuff, but for the most part, gas and stars. And the gas, over time, condenses into stars. This is how stars form. And as stars live, they basically fuse elements together and build up heavier and heavier elements. And then when they die, they release those elements into the galaxy. So over time, the galaxy gets enriched with heavier metals. And so this process happens multiple times over a galaxy's life. And so the properties that we study are ones that can tell us something about this cycle. So I study things like the stellar mass, which is the mass of the galaxy's stars, and that tells us how much gas exactly has condensed into stars. I look at the metallicity, which is, okay, so metals for astronomers are anything heavier than helium, which is not actually that much. So gas phase metallicity tells us how many times or how much the galaxy gas has been enriched by the stars. And it also tells us something about how the galaxy might interact with other galaxies. So inflows and outflows of gas from other galaxies or from filaments of gas can also change the metallicity. And then finally, star formation rate tells us how quickly this whole process happens. So galaxy properties is basically what I just said. The only thing here worth remembering is that SFR is an abbreviation for star formation rate, and it's one that I'll be using pretty frequently. So if you need a reminder, just feel free to ask. Feel free to interrupt also if you have any questions. Anyway, so we have these three properties, and what we want to understand is how do they relate to each other, and also how do the properties evolve over time. So going back to our lovely diagram, which I made in Microsoft Paint, you can see the relationship between these different properties. So we'll start with the one between the star formation rate and the stellar mass. So this has been really well studied by previous scientists. So here on the y-axis, you can see star formation rate, and on the x-axis is mass. And as mass goes up, star formation rate goes up. But as you can see, with time, you actually move down. So you start from red and you move to blue. So overall, you're moving to lower star formation rates. And this is something called galaxy quenching. So at some point, galaxies stop forming stars, and we have no idea why. This is one of the biggest open questions in extragalactic studies. So some people have different names for different theories for why this might happen. So strangulation, Yeah, these are all really pleasant names. There's other things like harassment and, choking. It's really nasty. But strangulation is when a galaxy's gas supply gets cut off, so it can't form any more stars. Or the gas within a galaxy is completely removed by other things, like maybe supernova shock waves, or giant black holes expending energy and then expelling gas. So we pretty much understand this. Well, we don't understand the physical properties behind it, but we at least understand the relation pretty well. So going back to our diagram, we can now pick two different properties. This time we'll look at the mass and the metallicity. And again, as mass goes up, so mass is here on the x-axis, metallicity, which is on the y-axis, goes up. And this is also really well studied, and it's shown that it evolves to higher metallicity over time, which also makes sense because as a galaxy lives, its stars continually enrich it so its overall metallicity increases. And this has a couple of different possible physical origins, which are also hotly debated. So things like gas outflows, maybe, again, these are the supernova that are expelling gas from the galaxy, or gas inflows. So maybe there are inflows of some other sources of gas that are somehow making this relation. But as you can see from this graph, this is the exact same graph as before, there's actually a lot of scatter here, right? And so people have started wondering, maybe the scatter, if you put all three properties together, can you get rid of this scatter? So here we've got color-coded by star formation rate. So this is the mass and the metallicity as before, but now the star formation rate is color-coded. And you can see there's a really obvious trend, right? And so people have put this together and made this relation, which is called the fundamental metallicity relation. And fundamental here means it doesn't evolve over time. So now this has become probably one of the most controversial topics in galaxy evolution. Is this actually fundamental, and why? So first of all, let's start with, why should we care if it's fundamental? If it is, then that means there's a single set of physical properties that drives galaxy evolution over time. And if it's not, then there's maybe multiple sets of properties, or something's happening that we don't fully understand. And so it changes our basic paradigm about galaxy evolution. So it's really important for us to understand, does this change over time or not? And so the way we can tell if something changes over time is to look at it in the past and look at it today and see if it's changed, which makes a lot of sense. And so just a quick reminder, I'm sure all of you know this already, but when you look back in space, you're also looking back in time. And that's how we do these kinds of studies. And redshift is the amount by which light gets shifted on its way from a galaxy. And it's a measure of both how far away you are from the galaxy and also how old that galaxy is, because light takes a finite amount of time to reach us. And so the problem is that the redshifts between 0.5 and 2, which, I mean, they're just numbers, it doesn't really mean anything, but that's about when the universe was half its current age to now. So this is a really important era in galaxy evolution, because this is when star formation peaked and then started declining. And we still don't know why this happened. Remember, this is going back to our galaxy quenching and strangulation and that kind of thing. But the problem with studying these redshifts is that when you're looking at emission lines in a galaxy spectra, the emission lines get shifted to a part of the spectrum where the sky absorbs light. So it makes it really hard to measure anything here. And so what we've done to get around this, I was working on this NewHa narrowband survey, which uses a ground-based telescope, but it has a narrowband filter, this pink thing here, positioned at a wavelength where the sky won't absorb light. So you can see here this gray line on the bottom is a measure of how much the sky absorbs. And right here, we've got this nice window where there's not a lot of sky absorption. And this happens to correspond perfectly with an H alpha. So H alpha is one of these emission lines that we want to study. And it's at a redshift of 0.8, which is right in this area that we want to really understand. And so to measure the properties of these galaxies, we end up using either the emission lines that I just talked about or the overall shape of the spectrum. Okay, so we can go into more technical details later if anyone cares. But in the meantime, we have a couple of questions. So, does this fundamental relation exist? And are we sure? So first, we need to find the relation. And we did this using planes because planes are easy to work with. So in the local universe, we see a really strong dependence on star formation rate, right? That's really obvious. You can tell that going from red to blue, or to purple, I guess, is over an increase of 100 in star formation rate, measured in some units. But when we do this for our own data, so this is the equation at the top is just a plane equation, and gamma is a parameter we're really interested in. So this is the dependence on star formation rate. And we just said that we saw a really strong relation for local data, so that's this point here. But ours, this is our data. This is way off. And these are, standard errors of 1 sigma, 2 sigma, 3 sigma. So that's more than 99% chance that there's something really significant in this difference. So maybe a fundamental relation doesn't exist. But the problem is, are we really sure about that? So there's this joke in astronomy, right? In most sciences, you have a bunch of data points and you draw a line through it, and that's how you study things. In physics, you have 2 points and then you draw a line through it. And then in astronomy, you're trying to draw a line through 1 point, which is completely useless. And that's because in astronomy, we generally have very small sample sizes, especially when you're going out to redshift of 0.8. So we wanted to understand, is our result due to statistics or something else? So we looked at the sample size, measurement uncertainties, and we didn't really find anything significant. But then when we looked at how we picked our sample, so different people pick their sample in different ways. In order to avoid noise contaminating their samples, they might say, well, we want our signal to be at least 3 times stronger than the noise. The problem with that is if you set your cutoff at different areas, you actually do get a huge effect, and that will significantly change your results. And then on top of that, there might be other things too. So maybe the way we fit our data was not very good, or maybe we shouldn't have used a plane, because if you go back to if you remember what the nice, pretty picture of the relation looked like, it looked pretty curved. It didn't really look planar. So our second conclusion is that we're not actually sure if this is fundamental, and there's still a lot of work left to be done. And in the meantime, we're sort of waiting on the big, space telescopes like James Webb to really give us the kind of data and the statistics that we need. And in the meantime, what I'm doing now is looking more deeply at these individual properties. So looking at the metallicity this is what I'm working on right now. We have a paper that's in referee purgatory. Where we're really trying to understand how people get metallicities, right? So when you look at a galaxy spectrum, which again is what we're getting all of this data from, you can see that there's a bunch of different emission lines of various kinds. So for instance, here's the H gamma line, and this is an oxygen line. And the question is, how do you turn that into a metallicity? What is the physical relationship between these lines and however many metals you have in your galaxy? Because you can't observe every single line. And so different people end up using different calibrations, just different empirical ways that they've figured out of calculating, approximate metallicities. But they're not really physical, and they're not really accurate. And so one of the things we're trying to do right now is study what we call direct metallicities. So ones that directly measure how many metals you have based on the temperature. Yeah, so it turns out it's pretty hard. And so this is something that we have maybe right now 300 galaxies, but the ones that we have any useful data for are like 60, 50. So again, we're having this issue with sample size. So in the future, what I'll be doing is working on star formation rate instead, because metallicity is actually extremely complicated, and you risk stepping on a lot of people's toes. So star formation rate is a little simpler. So star formation rate uses up gas. This makes sense, right? You need gas to make a star. And so you should expect a relationship between how quickly stars form and the amount of cold gas there is, right? If the gas is too hot, then it won't be able to collapse into a star. And if it's not dense enough, then there won't be enough material nearby to collapse. So as you might expect, as cold gas density increases, star formation rate increases. And this tells us how quickly gas is used up. The problem is that when people look at this relationship, so this relationship here, the one plotted, is for a bunch of different individual galaxies. But when people look at the same galaxy and plot different areas, they don't find this holds at all. It's a completely different relation. And so that's what I'm going to be studying next year with this guy, Kennicut. He's one of the 2 names in this relationship. Yep. So in summary, yeah, that was pretty short. For the NewHa alpha survey, what I was doing in the past was understanding the fundamental relation between galaxy properties, and we found that it might not exist, but there's a big question mark. Right now, we're trying to figure out how to better calculate metallicities in a galaxy, and in the future, we want to understand how does star formation really work on the galactic scale. Because it turns out after all these years, we still have no idea about any of these things. So, and then big picture, which I'm sure you guys all know by now, is we really want to know how we got here and how our own galaxy and galaxies like it formed the way, evolved from the beginning of the universe. Yep, so that's about it.
So I would like to ask a question because I know someone else is going to. I'll ask the first. How does dark matter factor in?
Yeah, okay, that's a really good question. So we know that galaxies, all right, I kind of lied in the beginning. Galaxies are made up of gas and dust, but actually it's predominantly dark matter. So our own galaxy has a huge dark matter halo that surrounds it. And so people have started to realize that dark matter might actually be the thing that's really driving star formation rate in a lot of these cases. And it might be driving things like metallicity too. So if you have a galaxy that doesn't have a lot of stars, but it has a lot of dark matter, then that will still pull in gas from outside, and that might affect the metallicities again. Or in the case of star formation rate, if you have too much dark matter and not enough gas, then you're not going to be able to form any stars because you can't form, as far as we know, you can't form stars out of dark matter. So yeah, it plays a huge role. Yeah, so that's the thing. It seems to be working in both directions. It might be a catalyst for star formation rate,
Right.
but it might also be shutting it down. And so what people are doing is studying the dwarf galaxies, the satellite galaxies that are surrounding our own galaxy. And because these galaxies don't have a lot of stars, that's why they're called dwarf galaxies, but they do have a ton of dark matter. And so this is what we're trying to, this is one of the, again, another open question in galaxy evolution. Yep.
Go ahead. No, when you say dark matter, you mean non-baryonic? Or
Yes.
You mean, okay.
Yeah. Anything we can't see.
Is there, you see that the gas can be ejected from the galaxy?
Mm-hmm. Yeah.
Is there evidence of that, and how does it show up?
Yeah, so we have seen evidence of what are called gas outflows. I think back in 2004, there was a paper release where people actually saw the remnants of the jet that expelled the gas.
It's the jet that's doing the outflow.
Yeah, so.
As opposed from the external parts of the galaxy.
Right, so this is.
Supernova.
Yeah, so again, a lot of these questions, we don't even have any idea because there are two main competing theories. One is that it's star formation itself that's expelling gas. So if you have really dense amounts of star formation rate, as the stars form, they blow away some of this gas and dust. And then the other is the jet at the center of a galaxy that's getting rid of the gas. And we don't know. There's evidence for both, and it might end up being a combination of both. That's my guess, at least.
How are you taking this data? What's your procedure?
Yeah, absolutely. So, so as I mentioned, we use for the fundamental metallicity stuff.
Well, I mean, I'm talking about the experimental design of all of this.
Right, okay. So what we do is we target galaxies, usually using known galaxy surveys, and we decide which ones are likely candidates for star-forming galaxies. Because in this work, we mostly avoided using the active galaxies, the ones that have an active black hole in their center. And so we find our candidates, and then we target them. Basically, we cut little slits onto the filter with that, and try and get spectra from that. And we use a GRISM, so it's a combination great and prism, and then you get spectra from these, which have some resolution based on your GRISM. And then from your spectra, you can calculate all these other properties. So it's basically, we're getting all this from spectra.
And where is the telescope that you're using?
So the one that we use for this one is in Hawaii. So we use the DEIMOS telescope to get our spectra, or the DEIMOS instrument on the Keck telescope, which is on Mauna Kea in Hawaii. Question in the back first.
Are elliptical galaxies examples of gas starvation?
Yeah, so that's actually the main point of galaxy quenching. We know somehow that a lot of galaxies go from being these really active star-forming spiral galaxies to being these really passive elliptical galaxies that aren't forming any stars. And that's the whole point of galaxy quenching, figuring out how they got from one to the other. Yeah. And then we have a question here.
Do you account for galactic age in your star forming rates?
Yeah, that's a good question. No, we don't. But if you can calculate, how do I put this? We don't. We assume we're looking at an entire population of galaxies. So overall, the star formation rate will either increase or decrease. And usually mass is a general indicator of age, right? So galaxies, we're pretty sure, build up from smaller galaxies to bigger galaxies. So the trend between the star formation rate and the mass could be seen as a trend between the age and the star formation rate.
Okay, and a question.
Yeah.
Most galaxies have a central black hole.
Yes.
Okay, so you're excluding those?
We're excluding the ones that have active black holes. So these are black holes that are actively accreting material onto them and then expelling jets of some kind.
Okay, so you just look and see if there's a jet and you.
Yeah, a jet or there are other trace like indicators. So at such a far distance, all of these galaxies look like point sources. So you can't really see if there's a jet, but you can look at the spectra, and the spectra will have some features that say there's something going on there. Yeah?
The chart that you had where you plotted all three variables together, I think one of the axes was metallicity, the other one was mass, and then you had different colored lines for
This one?
star formation rates.
Oh, sorry. This is, yeah. The one before this one? Or this image? Sorry. Let's make this bigger. Are you talking about this one? Oh, this one. Okay, yeah.
It's not coming up on the screen.
Oh, sorry. I wasn't even looking at the screen. I'm sorry. Okay. This one.
Yeah, that one.
All right.
Could you explain what the different colors represent on there?
Yeah, okay. So going from red, that's low star formation rate, to purple, that's higher star formation rate.
And so the x-axis is mass.
Yeah, so this is the same as the mass metallicity relation, but now they've also just considered star formation rate on top of that.
So could you explain how they interrelate on this?
Okay, yeah. So at a given mass, let's say mass of, so the way the axes work, it's a little strange. This is 10 to the 10 solar masses. So this is a really large galaxy. As you can see, if we cut across this slice right here, so for a given mass, as you increase your metallicity, as you go up, you decrease your star formation rate. Does that make sense?
So as you said, as you increase your metallicity, the star formation decreases.
Yes. And so overall, I mean, that's an artifact of galaxy quenching combining with, so it's just age, right? As a galaxy ages, its metallicity increases and its star formation rate decreases. But if the exact way that these properties relate changes over time, then that means maybe there's other properties or other processes that are helping drive this. Does that make sense?
So like when you have a red
Mhm.
star there, the star formation is lower.
Yes.
Purple or higher.
Mm-hmm.
You talked a little bit about a little more direct ways of measuring control speaking, measuring metallicity.
Yeah.
Can you maybe elaborate a little on that?
Right. So we call it direct, but it's still pretty indirect. What we do is we look for a spectral line called the O3 line. Basically, it's an ionized line. It's a line of ionized oxygen. In order to ionize anything, you need energy. And that energy is an indicator of temperature, basically. So that means if we see this line, if the flux of the line is bigger, then the temperature is bigger. Does that make sense? If we see more of these O3 ionized molecules, then the temperature is higher. And so that tells us something about the temperature. And then from simulations, we know that temperature and metallicity are inversely proportional. So as temperature goes up, metallicity goes down. So it actually ends up being even more, well, not even more. It's more direct than the other calibrations.
So usually, like it's like a trace.
Yeah, exactly. It's still indirect. We just call it direct because it's the best thing we have, which is kind of sad.
So you said just a quick follow-up.
Yeah.
As the temperature goes up, and then this will be.
Yeah, and that's just the general trend we see from our simulations, which again, might even be wrong. We don't know.
Just for the O3 or-
Yeah, so the O3 is the best tracer of it because it's one of the lines that we can actually see that's ionized. Some of the other ones are not possible to see, or they're so weak that it's really difficult. Yeah. Yeah.
You mentioned that dwarf galaxies have lots of dark matter.
Yes.
How can we know that?
So the way we measure the amount of dark matter in a galaxy is we see how fast the stars are moving, basically, in the galaxy. And since the dwarf galaxies are so close, we can measure this pretty directly, right? So we measure how quickly the stars are moving, and then if the stars are moving faster, then it can be accounted for by the mass in the galaxy. Does that kind of make sense? Sorry. If it's moving faster than what we see from the stars in the galaxy, then we know there's something else there that has mass and is making the stars go fast. Does that make sense? So things go faster around more massive things. That was a very hand-wavy explanation. That's basically how we do it.
So we're talking about like the Magellanic Clouds and stuff too. Are they like?
Yeah, so they're satellite galaxies. They're much bigger than any of the dwarf galaxies we see. So I think the Sagittarius dwarf galaxy is the biggest one known. It's pretty small. It's on the order of, oh man, off the top of my head. I think in order to measure the rotational velocities, they measured like 50 stars in the galaxy. And some of the other ones, they get even smaller. They measure things like, they measure 10 stars or 20 stars. But they know that because the stars are gravitationally bound to each other somehow, and they're moving fast enough that there's no way just the stars themselves are responsible for that, then there's a lot of dark matter there.
Is that particular galaxy the elliptical you're talking about?
So they're mostly irregular. They're either called dwarf spherical galaxies or dwarf irregular galaxies. And then spherical is used very loosely because, as I said, there's like maybe 20 stars in some of these. Yeah, or the ones that we can observe well. So. Yeah.
Any other questions? Okay, let's give her one more.